Hopefully you've had a chance to try these practice problems. I'm going to walk through the solution. So if not, just give it a pause and give these a try. So for this one, we're going to practice electron configurations, abbreviated electron configurations, orbital diagrams, quantum numbers, and valence electron configurations for 4 different elements, which is a lot, which is what we've covered recently. But they go so hand in hand that it should hopefully kind of go fairly smoothly. So let's start with iron. So iron has, let's do this. So iron has 26 electrons. And we can create its electron configuration from that. So I'm just going to start writing it out. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 before our 3ds. And then we have a transition metal for iron. So it's going to end in these d electrons, and it has 6. So there's 6 remaining. So here's our electron configuration. To report the abbreviated one, we would go to the noble gas in the 4th period, and so that's going to be argon, and it'll have the abbreviated configuration of 4s2, 3d6. Now, if I wanted to do the valence only, then I would be focusing in on that highest quantum number, which is the 4. And so the valence configuration would be argon to abbreviate, and then 4s2. All right, let's draw the orbital diagram next. So I'm going to have my energy diagram here, and I'm going to put in I can see that I'm going all the way up to 3D, so I'm going to write in my order of my orbitals. I've got 1s, and I have 2s, 2p, my 3s, 3p, 4s, and my 3d. And I'm going to stop there because I know that my electron configuration stops at 3d6. So I'm going to go ahead and fill these in. And I know they're all filled up until 3d. So I'm going to kind of just put the electrons in. I can be counting. But I'm not going to stress about it too much. And then I hit 3D and I know I have 6. So this is when I'm really going to pay attention to Hund's rule. I'm going to count out and fill each one of these with 1 electron first, and that gets me to 5. So I've got 1 more to place. So I'll come in and double up just 1 of the orbitals in the 3D. And that's my orbital diagram. Okay, so now we're going to do the quantum numbers for just that last electron. So that last one I placed in the 3D. So let's do our quantum numbers. We've got N, L, M sub L, and M sub S that we need to say. So that last electron was placed in 3D, so that's going to be a quantum number of 3. L is D orbitals, so L will be 2. Now M sub L, remember this is always going to be -2, -1, 0, +1, +2. And I'm seeing that that was placed in the first one, so I'm going to call it -2. And then it's the second electron placed rather than the first. And the first one always corresponds to a +1/2. So this will be a -1/2. And those are my quantum numbers. And that's iron. All right, we're going to move on to antimony. I'm going to get a fresh page up. All right, now we're going to do the same thing for antimony, which has a chemical abbreviation of SB. And looking at my periodic table, this has an atomic number of 51. So it's got 51 protons and 51 electrons. Okay. So for antimony, we're going to build out our electron configuration first. I'm going to start at 1s2, and I'm going to build up so that way I have a total of 51 electrons. So I'm just going to kind of put this out there. I know it's going to be bigger than iron right away. And if it helps, you can take a look at the periodic table to get an idea of how far you can go before you have to really start counting. An antimony is in the 5th row, and it's in one of the main group elements in kind of that P block. So I know I'm going to probably P5. So I'm going to start just putting these out in order: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, then we have 4d10, and then we'll have 5p. And looking at antimony, it's the third in the p block, but I can also count up my total number of electrons in my superscripts. And I see I need 3 more, so it'll be 5p3. If I want to abbreviate that, my closest noble gas is krypton, so I would make that Kr for krypton, and then 5s2, 4d10, and 5p3. And if I wanted to do just my noble gases, I would focus in on that highest N number, which is that 5, or sorry, not noble gas, valence electrons. So my valence electron configuration would be, I'm going to abbreviate krypton because otherwise it's really long, 5s2, 5p3 for my valence electrons. That tells me I'm going to have a total of 5 valence electrons, which is helpful when we do Lewis dot structures later on. All right, so with that information, I'm going to build my orbital diagram. And I know I have to go up to the 5 p's, so I'm going to make sure I give myself enough space for that. So 1s, 2s, 2p, 3s. And your spacing on this doesn't need to be perfect. 3p, 4s. What is important is getting the right number of orbitals for each one. So then we got 3d, got a ways to go. Then we'll have 4p. Then we have 5s2, and then we'll be followed by 4d. 1, 2, 3, 4, 5. Our d electrons always have 5 orbitals, and then 5p. That's a lot. Let's add 51 electrons. So doing that, starting at the bottom, I'm just going to fill these. I always fill them half first, even if I know that they're going to be totally filled. And that's honestly to stay in the habit, because a really easy mistake when you're learning this is to double up your electrons too early, and to have orbitals that are not filled with an electron at all, and others that are have 2 electrons in it, and then 5p3. So that's what my orbital diagram would look like. Last, let's do these quantum numbers. We have n, l, m sub l, and m sub s. And I'm going to do this again for that last placed electron in my orbital diagram or in my electron configuration, because otherwise we'd have to do a lot of these. And so that n level is 5 because we're at 5p, so that becomes 5. P corresponds to an L of 1. Now our M sub L, remember we go -1, 0, +1, so I'm going to call that one +1. And our M sub S is going to be +1/2 because it's the only electron in the orbital. So it'll be the first one added in, which we always do spin up. And then the second one added is spin down, just by convention. All right, and that's everything for antimony. Next, we're going to move on to carbon. So let's get that set up. So this one will be a little bit faster because carbon is not as heavy of an atom. And so carbon has an atomic number of 6, so it has 6 electrons. So if I'm writing out its electron configuration, it's going to be 1s2, 2s2, 2p2, 2, 2, 2. All right. Now, if I wanted to do the abbreviated one, I really can only abbreviate a little bit. I'm going to go to helium, the smallest but closest of our noble gases, which will basically abbreviate that 1s2. And I'll put 2s2, 2p2. And so that's our abbreviated version. Now, here's the beautiful thing. The abbreviated version, this one is also our valence electrons. Because we only have one of our quantum numbers, and it's the highest one, it's 2. So it's also our valence electron. It works for these much smaller ones. So let's build that orbital diagram. So I'm going to start with my 1s at the bottom, then my 2s, and now I only have to go to 2p, so I'll stop here and start filling in my electrons. So starting at the bottom, I've got 1, 2. I need a total of 6, 3, 4, 5, 6. So those 2p electrons both are unpaired, and they're both spin 1/2. So let's figure out those quantum numbers. We've got n, l, m sub l, and m sub s. And remember, we're just going to do that last electron so that way we're not doing this all day long. So we are at an energy level, an n quantum number energy level of 2 because we're in the 2p orbital. So that's 2. Our p's, remember, correspond to an L of 1. And so our m sub l is going to be, so if we set up -1, 0, +1 for each of our orbitals, it looks like it's in that 0 orbital. So we'll call that 0. And it's the first electron in, so it'll be spin positive 1/2. And that's our quantum numbers for carbon. All right, one last one. Let's do sulfur. So sulfur has 16 electrons in it. And so we'll start with writing out our electron configuration. So I always start at 1s2, then 2s2, 2p6, and this one's going to be in that third energy, or that third row. So I'm going to go up to 3s2 and then 3p4 for this one. So if I abbreviate that, my closest but smaller noble gas is neon. So it'd be abbreviated with the neon symbol. And then 3s2 and 3p4, which is also my valence electrons for my valence electron configuration, because I only have that 3 quantum number and it's the largest one in my abbreviated one. So let's look at that electron configuration. It looks like I'm going up to 3, so I'm going to have my 1s, my 2s, and followed by my 2p, then my 3s, and my 3p. And I'll start filling from the bottom up, and I've got 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've got 4 electrons in that p, of those p electrons, and so only 2 of the electrons will be paired up, and then 2 will be on their own in an orbital. And lastly, quantum numbers. Sorry. So we're looking at that last electron placed right here. So that's in the 3p orbital, so that n is 3. That L for p is 1. And our m sub l, we can come in and we'll put in our -1, 0, and +1. It looks like that is being placed in the -1, m sub l, or orientation. And since it's the second electron placed, it'll be -1/2 for its spin quantum number. All right, and that's sulfur.